Okay, YouTube, in this module, we're going to be focusing on the graphs of quadratic functions and how to graph them through their various forms and basically their characteristics. But we're going to start with this. A quadratic function we would say is any second degree polynomial that we're graphing here. But essentially, when we talk about a quadratic function, we're getting these graphs that we call parabolas. Okay, so these graphs that you see here, these U-like things, are called parabolas, even though it is a quadratic thing. So important things to recognize here. We're going to say that for something that is in this form here, y equals ax squared plus bx plus c, we would have a quadratic thing that is going to graph a parabola. But we want to write a note here. If a is positive, then what it's going to tell us is that this thing opens upward. Okay, so opens upward, and if a is negative, then it's going to open downward. Okay, and this is kind of key in our understanding of parabolas here, because we often use parabolas to model situations where we find a maximum or a minimum. Okay, so in this case, one thing I do want to note here is that we say if a is positive, it opens upward, as this illustration here. We also want to say that if a is positive, then it has a minimum value. Okay, and you can write minimum there, but I'm going to say it has a minimum, whereas if it opens downward, if a is negative, then it has a maximum value. And that's just going to be kind of clutch when we try to accomplish certain application situations here. So what I'm going to have you understand is this. When we talk about quadratic things, quadratic equations, they come in this package here, y equals ax squared plus bx plus c. And I'll write that over here as well. I want to make sure that we get it written next to what you see over here, because all of this is being explained in a what I'll call standard form here. So another thing I want to call this is standard form. Now when I say standard form, I really mean standard form. Most books I see, or people who communicate mathematically that I speak with at least, we refer to this as the standard form of the equation of a quadratic thing, whereas over here we say what you could really consider is that we're transforming the graph of the parent function f of x equals ax squared. And really what we end up with is a situation where we say f of x, instead of being ax squared plus bx plus c, we get is a times x minus h squared plus k. And this is a form we know really well. As a matter of fact, your textbook likely may sometimes call this standard form. And so what I'm going to tell you is that in this particular instance, I'm going to refer to this as vertex form, even though the examples that ask us to put it into standard form really mean vertex form. And we call this vertex form because, simply put, we would say the graph of ax squared, that's our parent function here that you see in black. So if we say that ax squared, which is this parent function in black, that starts at 0, 0, and goes through whichever point over here depending upon the vertical stretch, could open downward, could open upward, really what's happening is that we're shifting it h units left and right and k units up and down. So for instance, this parabola here went h units to the right and k units up from this initial point 0, 0. So one thing is for sure, if we've deviated h units and k units respectively from 0 and 0 respectively, then our vertex is always going to be at h and k. So that's written here. You might want to rewrite it, but this is very important. I'm going to rewrite it. We say the vertex is always at the point h comma k. And then also this, we would say that the axis of symmetry. This axis of symmetry is this imaginary vertical line that runs down the center of every single parabola. And yes, we need to draw it in every time, and yes, we need to label it. So this, for instance, here I would write as x equals h. It seems that it's listed here already, but the thing we want to admit is that the axis of symmetry is always at x equals h if this is in vertex form. So since we're already kind of familiar with vertex form, what I want to do is I want to be able to graph a couple of parabolas here given their equations. But before we do that, let's really quickly visit a few things in terms of what we want to know. We want to know the standard form. I'm going to cross this out and say vertex form, the vertex form of a quadratic function, as well as the steps we're going to take to graph it. So we say this quadratic function right here, where we know h and k are our left and right and up and down shift respectively, and a is either reflection over the x or stretch or shrink vertically. But we say the graph of f is a parabola whose vertex is the point hk. The parabola is symmetric with respect to the line x equals h. We're going to refer to this as our axis of symmetry. And then we say if a is positive, it opens upward. If a is negative, it opens downward. So in terms of graphing this, the steps we're going to follow are simply these. We're going to determine, first of all, before anything else, whether this opens upward or downward, whether or not a is positive or not. The next thing we're going to do is we're going to determine the vertex of the parabola. So now we know whether it opens up or down, and we know where it begins. So last, few steps here, find any x and y intercepts. Now here's an important note here. We say when you find an x-intercept, then what you're finding are all the x values that cause your y values to be 0. This is really y right here because this is y. So we say the function's real zeros are the x-intercepts. So notice that we're calling them zeros, okay? X-intercepts, those are the same things. And then to find the y-intercept, we'll just plug in 0 for x and find y. Okay. And then last but not least, we're going to plot these intercepts, the vertex, any additional points, and connect it with a nice smooth curve. So to enact all of these steps here, I've got a couple of examples. We're going to start with this quadratic function right here. So I want to identify a few things. First of all, a, h, and k. And so our a, h, and k values here. Our a value seems to be a -1 out in front. H is seemingly backwards. Don't forget about that. But it's a positive 1 where our k value is actually not lying to us as a positive 4. So using all of this, what we know is that our function here is just going to be right 1 up 4 from the initial parent function. It's going to be shifted there. And because it is shifted to there, we would say then the vertex would be at that h and k pair. We could just say 1, 4 just by looking at these two values right here. But I'm going to label this, and because also I know that this opens downward, I'm going to label it on top. So here's what I want everybody to see. The first two steps we just completed kind of hand in hand. And that is to say that a first step was to see whether it opens up or down. If I can flip back here a slide. See whether it opens up or down, and then find the vertex. So you kind of do those things together. You notice I labeled on top here. The next thing I want to do is I want to make sure that we put the axis of symmetry running down the middle of this. It's kind of a key part of every parabola. And we're going to label this. Since it's a vertical line, it's x equals a number, and it always has to have the same x value as what your vertex is. So it has to be the same here. Okay. Also, y-intercept and x-intercept. Now I think it's easier to find the y-intercept. And the reason why is because we're plugging in 0 for x. So when we say 0 for x, what we get is this. We say f of 0. And f of 0 in this case is -0 minus 1 squared plus 4. So when we plug this in, it looks like we get a -1 squared. So we get -1 squared plus 4. So -1 squared is a positive 1, but then we get -1 there because of the negative in front. And then we would get -1 plus a positive 4 is a 3. So we would say that that 3 right there is where we hit the x or the y-axis. That's our y-intercept. Okay, and so we say 0, 3 is on this graph. 0, 3. So we want to find the x-intercepts, and because I know that the vertex is here, I can kind of get this idea that it probably swings down and looks something like this. Now I'm not sure exactly what it looks like yet, but we're going to make our picture a little bit bigger. And by the way, I should put that 0, 3 here. Now what we're going to do is we're going to find the x-intercepts. And so to find the x-intercepts, here's what we're going to do. We're going to set this whole thing equal to 0 and solve it. And by set it equal to 0, I really mean we're going to plug in 0 for our y values, because remember, our x-intercepts here are where our graph intersects the x-axis. So I'm going to set all of this equal to 0, and we're going to solve this. Now, solving this, because I know that I have just this squared quantity right here, I can get it by itself and use square roots to solve it. So I'm going to start by subtracting 4 from both sides. We would get that -4 equals negative in parentheses x minus 1 squared. And so now I'm going to divide everything by a -1. This is going to make this on the left here a +4, and this is going to be equal to now x minus 1 squared. So now at this point we can just take the square root of both sides. And so on the right side we get x minus 1 perfectly. On the left side we get plus or minus 2. We were lucky, you don't always get a perfect square in your square root. But then the last thing we want to do here is just add 1 to both sides. And I'm pretty reluctant, or not reluctant, but adamant on how I like to write this here. But I'm adamant that I like to write the constant before the plus or minus here. So I'm going to put a box around this. But these are our x-intercepts here. And I'm going to simplify it also. 1 plus 2 is 3, and 1 minus 2 is -1. So our two x-intercepts are these. We would say that -1, 0, and I'm going to write an and there. So you know it's not interval notation. We're writing points. And those right there. So I could say that at -1, it hits the x-axis. And look at that. This is a pretty good sketch. Sorry, I tooted my own horn here. And then 3, 0. We've got those on the graph. So now what I would say is the best possible policy is to plug in a little bit more in terms of x values if you're missing any. Like I might plug in 2, and you would get a y value here. Actually, because of symmetry, though, we know this would be right here. And actually because of symmetry, and I say that these graphs are only really interesting in and around their vertices. Around on the edges, they're just going to really decrease without bound here. But basically, because they're only really interesting on the inside, you only need a few points, your vertex, and at least a couple points on each branch. I'm going to say that we're going to get in the habit of finding x-intercepts here. But then you can make the rest of the graph, okay? So our domain looks like -infinity to infinity, and then range, it looks like we start way down at -infinity, and then we go up to this maximum height of 4. And that's one thing that I do want to mention here, that indeed was a maximum, but because our parabola opened downward. So we're going to try this again, a little bit faster this time. but we're going to be given a new equation here, f of x equals x minus 2 quantity squared plus 1. Let's start with whether it opens up or down. So we could say that this thing opens upward. And the reason why we know this is because our a value here, which is equal to 1, is greater than 0. It's positive. So we want to find our vertex next because I know that it occurs at h comma k. And I witness that we have each of these values. We say 2 comma 1 is our h and k here. We're also going to shift right 2 up 1, which is what our function would imply. So now that I know this opens upward and it shifts to, to the right 1 up, I'm going to label it kind of underneath, and I'm going to make sure that I put our axis of symmetry on here next. So the axis of symmetry. Well, the nice thing about this is that it always runs through the vertex. And so it's got to have the same x value. So x equals 2, and we want to label it with an x equals a number. So now our y-intercept. Well, this is great news because we can just plug in 0 for x and get our y-intercept. So we say plug in 0 for x to get the y-intercept. We get this, 0 minus 2 squared plus 1, or negative 2 squared plus 1, or 4 plus 1, or 5. So we would say 0 comma 5, or 5 up on our y-axis here is going to be our y-intercept. That would be reasonable to go through that right there. And then we would say our x-intercept. Let's list our x-intercept here. We're going to find that by solving this equation, which means set it equal to 0, set our y value equal to 0. We're going to solve this. And again, I'm going to use square roots here. So let's get the squared thing by itself. We get x minus 2 squared equals negative 1. And then I'm going to take the square root of both sides here. So I get this. On the left side, I get I times the square root of positive 1 equals x minus 2. And I want to comment on this here. Because when we take the square root of 1, we get plus or minus 1. This is just plus or minus I. And that, when we add 2 to both sides, I'll just put it right there, we get this. We get x equals 2 plus or minus I. Now, the fact is that these are non-real x-intercepts, which means basically that because we knew that the vertex was right here, and because it opens upward, we can kind of get this idea that it's a U-like shape through here. I'm going to do a better job when I actually sketch it here. That it's never going to hit the x-axis. So we're going to write, and I'll write in red letters here. Actually, I'll write in red letters and all capitals that there are no x-intercepts here. But the way you're going to be able to tell algebraically is the fact that you ended up with non-real results. So I could have told you right there you're not going to get any x-intercepts. So in terms of graphing the rest of this, well, I would say that just because of symmetry, I know that if I were to go left 2, I'm going up 1, 2, 3, 4 from the vertex point. If I go right 2 and I go up 4, that this point's also going to have to be on my graph. So if I go right 2 from our vertex point, we'd be at 4, and up 4, I'd be at 5. And that makes reasonable sense. It'd be the same height as 0, 5. And then also because our a value here is 1, then I know that from this point as I go right 1, I'm going to go up 1 here. And because of symmetry, this is also on our graph. So without plotting really any extra x values, we could say that our parabola looks like this as a minimum value, okay? And its domain is negative infinity to infinity, while its range here, it looks like it has a minimum value of 1 and then goes up to infinity. Cheers.